Hey everyone, so we are going to have a two-part review for the final. The first bit here will just be me reviewing some of the material that you're going to need. It's basically just going to be everything from the first and second midterms. The third midterm for this semester, we just did a lot of data visualization stuff. That's not going to be on the final, okay? So we're just going to need to study midterm 1, midterm 2 material. So what's best for studying that? We'll certainly take a look at your notes, the in-class exercises, your homeworks, but also check out the first few chapters of Wooldridge. Wooldridge really explains a lot of this stuff really well. So if you can go through his book, it's a little technical, theoretical, which isn't super fun, I know, but it's certainly a wealth of knowledge. So if you can understand what's in that book, you are going to be golden on the exam. Okay, so let's take a look at some of the key statistics we're going to be using on this first bit of the final. So if we include a hat, that means that we're taking the mean of that variable. It's the mean of the variable. So we just say the mean is just 1 over n times the sum of all the observations of that variable, okay? And we use that notation whether or not it's y, so y hat is just, or excuse me, y bar is just a mean of y, and if we just put that hat on x, it just means the mean of x, okay? So that's really important to make sure we get these building blocks early on, because we need those to build our other bits, okay? So next bit we're going to look at is beta 1 hat. Okay, so the hat basically means that this is an estimate. Okay, so we'd like to have this value of beta 1, but we don't know what it is. It's a population value, it's unknown, but we can estimate it with beta 1 hat. Okay, so specifically what that value is, it's the slope of our regression line. And I give you an interpretation for it. Okay, so you're obviously going to be asked about interpretation for this, and if you just follow this to a T, unless you're using logs, so for not using logs, if you follow this interpretation, you should be good. If x variable, whatever it is, increases by 1 unit, the average associated change in the y variable, whatever that is going to be whatever beta 1 hat is. Okay, so as far as calculating it goes, obviously, at least for simple linear regression, we are going to need to calculate this. Since there's not much I can do for stopping you from using the regression calculator that I gave you guys before the pandemic started, I'm going to give you less points for this bit. So I definitely focused a good bit of that of the first exam on giving you a lot of points for here, so I probably won't do that as strongly as I did on the first midterm, but I will probably at least get you guys to try to calculate this beta 1 hat. Right? So it's just basically this bit here. Okay, but we can actually make it slightly easier, and if you want to remember exactly how we kind of shortened that, check out the review from the first midterm. I did go over that. I might have it still in this midterm. I might have copied that over. I can't remember. But regardless, this is going to be our shortened version. So remember this sigma here, that just means sum. So we're summing up at each observation xi minus x bar. Okay, so each observation's x value minus the average x value, and we're multiplying that by the y value for that observation. Okay, and that's going to be all over the sum of xi minus x bar squared. Okay, in other words, what this really is it's the covariance between x and y over the variance of x. Okay. Next, we're going to have beta 0 hat. Again, it's a hat, so it's an estimate. And that's just going to be our estimate of the y-intercept of this regression line. Okay. We have an interpretation for this. Which again, just follow this to the T, and you'll be good. If the x variable, whatever it is 0, then the expected value whatever the y variable is this beta 0 hat. And we estimate it using this. So this is a lot more simple than the other one. We just take the mean of y, so y bar, minus this beta 1 hat, which we just calculated in last turn. And of course, that means we need to calculate beta 1 hat first, times the average of x. And that's it. So beta 0 is a good bit easier to calculate, assuming we calculated this beta 1 correctly in the first place. Okay. We also have these estimates of y, these predictions of what y would be, and they're generated by beta 0 hat and beta 1 hat, and we would call this y hat I, really, because what we're doing is predicting what y should be at every level. Okay, and we would just find this by just saying, well, what's beta 0 hat plus beta 1 hat times whatever x is, and that's going to give us a prediction of yi. And through that prediction, we can kind of learn a little bit about our model. We can compare it to the actual yi, and if we do that by subtracting yi hat from yi, we get what's called the residual. Okay, so it's just the difference between our prediction and the actual data. So, for example, if we had our observations and we've got a regression line, the residual is just the difference between our estimate, which is on the line, and the actual value. Okay, so we're going to have a residual for every single observation that we have. Okay. We also square that residual, and in fact, that's kind of how we kind of motivate our formulas for beta 0 hat and beta 1 hat. If you want to take a look at that from your notes, that's actually kind of how we motivated how we got those formulas in the first place. Is we wanted to minimize this squared residual. Okay, so minimizing that squared residual actually, think about what that's doing. If we're making that as small as possible, that means that the difference between all of these points and our estimate is small. Now that sounds like it's a good thing, right? As far as matching, fitting our model. So that's what we want to do, is we want to minimize that sum. Okay, so that's actually how we motivated how we got this beta 0 and beta 1 hat. Okay, and speaking of fitting things well, we have a measure of how we're going to fit these things well, or how well we're fitting these things. It's called R squared, and that, as we've seen for a lot of our other statistics, has interpretations. Okay, so starting here and here. So if I ask you to interpret R squared, you need to use this exact, or something close to it. I'll have these, probably have these on multiple choice. So we'll have something here, and I'll ask you to interpret it. How do you interpret this? And you're going to need to tell me. And it should be something that looks like this. Okay, so R squared times 100% of the variation in whatever this y variable is can be explained by our model. Okay, and this wording is actually good for the single linear regression version and the multiple linear regression version. We could say in the simple linear regression version that it can be explained by whatever our x variable is. But if we another version of saying that is just saying by our model, and that actually works with our multiple linear regression as well. So how do we calculate this R squared? Well, to do that, we're going to need to break up some components of the calculation a little bit. So we've got all these squares. They've got these total sum of squares, the explained sum of squares, and the sum of squared residuals, which is this. Okay, so we've got these things, And let's break them up a little bit. So we already looked at that one. It's just the sum of the squared residuals, but we've got these other components too. So what is the total sum of squares? Well, it's just the difference between yi and y bar squared. What is the explained sum of squares? So this is the amount of variation explained in our model. And that explanation comes from our difference between the y bar and our estimate of what y should be. Okay, so that's what the explained sum of squares is, and our r squared is just the ratio of the total sum of squares, so the total variation in our model, and how much of that total variation is explained. Okay, so if we can calculate the explained sum of squares, just put it over this total sum of squares, and you've got the answer. And there's an alternate way to do it, and that comes from the fact that we have this equality here. So we just do a little bit of rearranging, and we would come up with this. So I did that in class as well. You don't really have to do that if you don't want to. You can just use this. They both should come out to the exact same number. If you get extra time in your exam, sure, feel free to run it more than one way. It's a good way to double check your work. If you see that you don't have the same answer for both of them, you might have made a mistake somewhere. So this should always come out to the same solution. Okay, and this is just a little bit those equations broken out a little bit. Okay. All right, so we also have a second interpretation for this, but this only works for simple linear regression. This is actually equal to the rho squared. So that's where r squared comes from, rho squared, which rho, as you may remember, is the correlation coefficient. Okay, so basically this is very similar to correlation. Okay, it's just the squared correlation number. Okay, so yes, I did actually have some of this extra stuff on here. I'm not going to really kind of waste your time on here. This is just some stuff that people had asked me about before, and I kept this on here. So this is just a few kind of things you might want to take a look at just to get your practice back in doing some of this, since it's been a little while. But this is nothing. I'm not going to make you do any proofs or anything like that on the exam, so I wouldn't worry about it too much, other than maybe know this stuff just so you can feel comfortable enough with the math to really feel like you understand it. But I'm not going to spend too much time on it because I don't think we're best served for doing that. And here's also that bit that I was explaining of why this equals this. But again, that's something I'll leave to you to do. I also included a little table for an example for doing simple linear regression by hand. So take a look at this example. Make sure that you can do this by hand and compare to the calculator. So let's go over some of the assumptions of simple linear regression. So first assumption is SLR1, linear parameters. Beta is our parameters, all right? So if our regression is y equals beta 0 plus beta 1 x, so this is our estimate. That looks an awful lot like y equals mx plus b. So yeah, this is linear, right? So that's fine. And we talk later in the semester about some nonlinearities and such like that. But even in those cases, our parameters are linear. Okay, so our beta is linear. But when we talk about that nonlinearities, we might have a beta for x squared, for example. Okay, well that's fine. Beta itself is linear. Okay, we didn't say anything about the variables. We just said the parameters are linear. Okay, random sampling. Okay, so why would it be a problem if we didn't have random sampling? Well, what if some part of the population is getting sampled more, or what if worse? What if you're sampled and maybe that could have some sort of a bias? So for example, what if people are sampling in a cancer hospital, and you're basically sampling of how do you feel today for the entire city, right? Well, if people are really sick, then they might not be feeling so good, right? So the sample that you're getting in there for this particular city it's not going to be very good, right? So we want to make sure we're having some sort of random sampling. We need to have random variation in X. So if we go back up here and we see that if we did not have random sampling in X, well, that would mean all these xi's are the same. And if all those xi's are the same, then their mean is going to be the same. And so we're going to have a bunch of a sum of the same number minus the same number squared. But if this is going to be the same number minus the same number, that's going to be 0. 0 squared is 0. So we're going to be adding up a whole bunch of zeros, which is going to be 0. And the problem with that is, well, that means we're dividing by 0. We can't do that. Okay, so we can't divide by 0. So that's just a rule for us to make sure that we can actually perform these calculations. Zero conditional mean. So in real life, this is one of the probably the reason we have econometrics. This is a very commonly violated assumption, and this is when we have residuals not being correlated with X. So when is that happening? Well, remember the residuals. This error is picking up all this stuff that's not in our model. Okay, so if our real model for calculating some y looked like this, plus beta 1 x plus, let's call that beta 1 x1 plus beta 2 x2 plus anything else. Okay, so if this was what our model really should be, but we don't have x2, so we don't have the x2, so we're just a simple linear regression, so we only are having one variable. Well, that means that some error term that we're using for our model, our residuals, includes both our random residuals and some non-random residual. Okay, so if this x2 is correlated with y, which it should be if we say it's part of the model, but if it's also correlated with x1, which is quite likely, then as x1 changes, this error term is going to be changing. And so that is going to be a bit of a problem for us for a few reasons. So we're going to assume that is not happening.